The time has finally come for us to begin discussing the concept of angular momentum in quantum mechanics. We could not do it before because we lacked a lot of the mathematical and physical understanding that we needed in order to just look at this concept. So why do we care about angular momentum in quantum mechanics at all? Well, the answer to that is that angular momentum is one of the fundamental quantities in physics that is many times conserved. So it's interesting to know whether this quantity is conserved and also just measure the angular momentum of some quantum mechanical states. And also, as we'll see, I will not spoil it for now, but it will introduce a new concept that is going to be very, very important. Now, I won't spoil it for now. If you know what I'm talking about, you know. But well, so we want to introduce this concept of angular momentum. How can we go about it? How can we examine quantum momentum in quantum mechanics? Angular momentum, sorry. Well, let's begin by talking about just what we know from classical mechanics. There we have defined the angular momentum to just be the cross product between r and p, right? The position vector and the momentum vector. If we consider Cartesian coordinates, we can just go ahead and write the position vector as x in the I hat direction. You can also call this x hat, but personally I like to use I hat more, but it doesn't matter, plus y in some j hat direction plus z in k hat direction. And the momentum, this is usually, well, remember we are now in quantum mechanics, so we have to include this h bar over I, and this will be factor of partial derivative with respect to x in the I hat direction plus partial derivative with respect to y in the j direction plus, and now comes the partial derivative with respect to z in the k direction. So let's take this cross product. So this is going to be the determinant of I hat, j hat, k hat, and x, y, z. Here, just for brevity, I will write px, py, pz, and later I will plug back each one of these values. So in the I hat direction, we're going to get x, py, oh, sorry, that's incorrect. It's going to be y, pz minus z, py. Here I can change the order because these quantities commute. If you want, you can check. It's just because this derivative on the y direction does not act on this z coordinate. Then we get minus j hat x pz minus z px, and finally we get plus in the k hat direction. There we have x py minus y px. So let us write down each one of these angular momentum coordinates explicitly. So just this modulus of Lx, what is going to be? So basically just this right here. Let's call this Lx. So that it's going to be y, then we have h bar over I d dz minus z h bar over I d by dy. So let's factor out the h bar over I. So we get y d by dz minus z d by dy. So this is going to be the angular momentum in the x direction. Similarly, let's take a look at the one in the y direction, which is going to be this. But for that, let's include this minus sign in here. So this will be positive, this will be negative. So we can factor out the h bar over I, and then we have z d by dx minus x d by dz. And finally, in the z direction, we're going to have h bar over I, and then we have x d by dy minus y d by dx. Okay, let me take this to the next page. So now we have, well, I'm covering up a little bit with my camera, but you already know what it is. I'm going to put it closer together. Okay, so now we know what the form of each one of these is. It's actually quite similar to what you may have seen in classical mechanics, except for this h bar over I. how can we now proceed? Notice that each one of these is an operator, right? If you apply this on some state, on some vector, you are going to get a different one. That's what we defined as an operator. So it would be interesting to see what the eigenvalues of these operators is going to be, because since, and you can check it, these are Hermitian operators. So if you take the eigenvalue of a Hermitian operator, that's going to be something that you can expect to measure. So we would really like to know what their eigenvalues are. So in order to do that, let us now begin to see, well, what can we know about these quantities at all? So for example, could we measure some of these simultaneously? Now remember, what does it mean to be able to measure something simultaneously? What does it mean that we can measure an operator and another operator simultaneously? That means that they have to commute. Okay, so let's see if Lx and Ly commute. So remember, this is just Lx, Ly minus Ly, Lx. So let me now put the values. Well, first of all, because there's an h bar over I here and here, I'm going to factor it out. So h bar over I squared. This is going to be multiplying this right here, y d by dz minus z d by dy. And then we have the Ly part, z d by dx minus x d by dz. And then we have, I think I'm going to run out of space. I thought it was going to be enough. I'm just going to take it here. Okay. And then we have minus Ly. So z d by dx minus x d by dz times y d by dz minus z d by dy. And remember, whenever we want to actually find the value of I'm missing a parenthesis here. Okay, whenever we want to find this commutator, we need to let it act on a test function. At the end of this procedure, we will eliminate this test function because it is only a test function. We don't care about that function itself. But it is important, as we have seen when we discussed commutators. So let's see now, let's do this product. So we get h bar over I squared, product of, let's see, so we got y d by dz of this. So y d by dz of z df dx. Okay, I'm going to let the f be acting on each one of these. Okay, so let's now do this partial derivative, and then I will replace it. So we have y, and now we have to apply the product rule here. So first let it derive z, so we get df dx plus y, and now it's going to act on the derivative, so we get yz, second derivative f, and it's z and x. Okay, so that's what this is equal to. So let's just write this. Okay, so now we multiplied this and this. Let's now go with the next term. So we get minus y d by dz of x df dz. But x is not affected by the partial derivative with respect to z, so we can just take it outside and we can write this like this. It was derivative in which direction? Sorry, it was in z. Okay, so it's actually second derivative in z. Okay, so I'm going to move it there. Okay, now we have the first two terms. Let's now go with minus z dy times this part. So we get minus z, and now the partial derivative with respect to y will not affect this z, so it's just going to be z squared. And then we have d squared f dy dx. Next now we multiply this and this, so it's going to be plus z, the x can go outside, so we get zx d by dy of f, and there's another derivative, so it's going to be squared dz. Okay, this part might be a little bit tedious, but make sure to go through it step by step so that you can avoid making any unnecessary mistakes. Now let's do this second part. I'm going to change colors. Minus, first here, z d dx, y dt. So y is not affected by this derivative, so we write minus zy d squared f dx dz. Next we have this one, so we get minus minus, so it's going to be positive, so we get z squared d squared f dx dy. Now multiply this and this, we get minus minus, so it's also positive. We get, let's see, x, you can get it, we can take the y outside, so it's going to be d squared f dz squared. And finally we got minus minus minus, so just minus x, and here we have once again what we are going to get two products because it's d dz of z df dy. So this will give us on one hand just x times df dy when we apply the derivative to z, and we will also get minus xz d squared f dz dy. And now notice that some of these quantities will cancel out, so we got yz zy dz dx dx dz, but all of these things commute. Two scalars commute, and the cross derivatives, they also commute. So this right here is the same as this, and for that same reason this is the same as this. And then we have this, which is the same as this. This is the same as this. And let's see, I think that's all. So let me just erase all of these things. Okay. And I need to close the parentheses. Okay. Now what do we have? Let's now take the test function outside of this, since we are now nearing the end of this part. Okay, what do we have? So let's take a look at what we have here. This is y d dx minus x d dy, and take a look at what we have here for LZ. It's x d dy minus y d dx, which is quite similar to this, except that it has the signs are flipped. So let's actually factor out a minus sign. So we get minus h bar squared divided by I squared, and then I wrote it kind of weird, but it's fine, and x d dy minus y d dx. So we can actually see now this is the same as this, except it has an extra minus h bar over I, and it still has this f. So let's now write it as minus h bar over I of Lz acting on this test function. And this, what is it equal to? This is going to be equal to the commutator of Lx Ly acting on this test function. But let us now just drop the test function. But we are now nearing the end, so we don't really need it anymore. And this is technically correct, but let us write it differently. Let us write it as h bar times I times Lz. Right, because you can just put this I up here and change the minus sign to a positive. But it's basically multiplying times I over I. That's how you get it. And this is the commutating relationship for Lx and Ly. And since it is not zero, it means that these operators are incompatible operators, which means that we cannot observe both of them simultaneously. So if we want to study this, we would like to find some other quantities that we can observe, not only this particular angular momentum one. So let us take a look at the operator L, right? Well, if I'm calling it operator, maybe I should put the hat over it. But this is just going to be the total angular momentum, which means Lx plus Ly plus Lz. Okay, now let's see, does this commute with any of these components? So L and Lx, for example. Obviously, and by the way, I just saw the commutating relationship for Lx and Ly, and in the same procedure, you can actually see, for example, Lx and, or actually, let me do it in order. So you can go for Ly, Lz, and you can go for Lz, Lx. And obviously, because of the properties of the commutators, this is the same as minus Lx, Lz, and this is the same as minus Lz, Ly. And this right here is just I h bar Lx, and this right here is I h bar Ly. So you can see that the result of the commutator is basically I h bar, and then I'd like to visualize it like this. So if you have x, y, you get the third one if you go in to the right, and then if you have y, z, you get x. If you get x, y, you get z, y, z, x, x, y, z, right? You're just going in this direction. But if you have y and x, you're going to the left, so you have to put a minus sign in front. So that will be minus Lz. So if you go to the right, you have a positive sign, and you go, if it's x, y, you get z. If it's y, z, you get x. If it's, that way. And if you go to the other direction, it's going to be negative. So that's the way I see it. So, and you can show this either just by cyclic permutation of the indexes, or you can just go ahead and do the same calculation that I did but for the other ones. Okay, back to this. Let's now write for L this form. So we get Lx, and going one step too far, Ly plus Lz, comma Lx. And because of the properties of the commutators that we discussed in a previous video, we know we can separate this into three different commutators, which is going to be Lx, Lx, Ly, Lx, and Lz, Lx. Okay, so now remember, every operator commutes with itself, because this right here is just Lx, Lx minus Lx, Lx. So that's just 0. So this first part right here is just 0. What about this? This is yx, and this means we are going from right to left. So we have to, this is going to be minus I h bar Lz. And this one right here, this is going from right. I guess this is going the right way, right? This was going in this direction, this is going like this. So this one is going to be positive. So that will be plus I h bar Ly. So this is clearly not 0. This means that the total angular momentum operator is not going to be a compatible operator with any of the Lx, Ly, Lz operators. So that's not good. So let us try something different. Let's now try, okay, what about L squared, which is just the square of the total angular momentum. You get it by squaring all of these components. What about this? Maybe this is going to be better. So let's see if it commutes with any of them. I'm just picking Lx. You can pick Ly, Lz. You are going to get to the same conclusions. This will be Lx squared. Actually, let me go step by step just in case. Ly squared, Lz squared, comma Lx. So once again, we can separate all of these commutators. So we get Lx squared, comma Lx, plus the commutator of Ly squared and Lx, plus the commutator of Lz squared and Lx. So the first commutator here will be 0 once again. This is just going to be Lx, Lx, Lx minus Lx, Lx, Lx. Okay, so this is just 0. This one right here, now we have to apply some properties here in order to make this easier. So I actually mentioned this one in the video about the commutators. We can write this as Ly, comma Lx, because this is basically Ly times Ly, which is like if you have the commutator of AB, comma C, and you can write this as A commutator of BC plus, I don't have much space left, I'm going to write it down here, plus commutator of BC A. Okay, so that's what I'm going to use here. So in this case, A is just one of the Lys. So it's going to be plus commutator of Ly, Lx, Ly. And why do I want to do this? Because we know what this commutator is, right? So it's going to be much easier to solve now. And then I have this part right here. I'm going to use the exact same property. So it's going to be Lz, commutator of Lz Lx plus Lz Lx and Lz. Okay, so let us now plug in the value for each one of these commutators. So first we have Ly, that's unchanged. And now we have this commutator. What it's going to be? It's Yx. This is going in the wrong direction. So it's going to have a minus sign. So it's going to be minus I h bar. And here's a y, here's an x. So it has to be Lz. It's always the one that is not here, right? So then we have plus, now comes this. This is once again, so actually let me just write it immediately as a minus. So minus I h bar Lz Ly. And it's very important, make sure to respect the order in which these L's appear. So you can't just commute them, because remember, they do not commute. Ly Lz is not the same as Lz Ly. So sometimes when we are just starting with this, you don't even think about it and you just swap it sometimes. But you have to be careful not to do that. Okay, so next one here we have Lz, and now this commutator. This one is in the right order, so it's just going to be positive. So I h bar Ly. And finally we have, once again, I h bar Ly Lz. So let's see what we have. So here we have minus I h bar Ly Lz, which is the same as here, but this is negative. So this cancels out this. And here, this cancels out this. So this commutator is actually 0. So that means that L squared commutes with Lx. And in fact, if you can see that it also commutes with Ly and Lz. And that's actually quite useful, because now we have something that tells us about the square of the total angular momentum. So now we know, we can't know the angular momentum in all directions simultaneously, but we can know simultaneously the angular momentum in some direction and also the total angular momentum, at least the square of the total angular momentum. So that's quite nice. So let us now work with that. And remember, our goal is going to be to find the eigenvalues, and that's actually something else that is very important. So let's pick as our operators of interest this L squared operator and Lz. Why Lz? It doesn't really matter. You could pick Lx or Ly, but it is conventional that all textbooks pick the z direction. All that I'm going to do works exactly the same in any direction. So you could pick z, x, y, it's up to you, but I'm going to stick with the convention and just use Lz. So these two commute. L squared commutes with Lz. Okay, so what does this mean? On one side, you can measure them simultaneously. On the other side, something else that is very important, this means that they can be simultaneously diagonalized. This means that they can have the same eigenfunctions, right? So if we have L squared acting on some function, this is going to give us some random eigenvalue times the eigenfunction. And if we have Lz acting on the same eigenfunction, this is also going to be its eigenfunction. So we are also going to get just some eigenvalue times the eigenfunction. Okay, so that's going to be very, very useful. So what I'm going to do, because as I said, what we want to know is what are these eigenvalues. That's going to be our goal. Okay, so we are going to use something that we actually have used before when we solved the harmonic oscillator, which is going to be a ladder approach. So we are going to use raising and lowering operators, just as we did back then. Now this can be weird at the first or even the second time around, because it's like, where do you get these raising and lowering operators? And it is hard to give a good intuition behind it as to where this comes from, more than just looking at the algebra and realizing that this has some particular properties, or maybe looking at how this resembles what we did back then with the harmonic oscillator. So we are going to define two operators, which will be the raising in the case of the plus and the lowering in the case of the minus. For now, the name doesn't mean anything for us, but we are going to define this to be Lx plus or minus y Ly. If this notation confuses you, just remember these are two equations in one. On one side, this is an operator called L plus, which is going to be Lx plus I Ly, and on the other hand, it's going to be L minus is Lx minus I Ly. Okay, this is just a way to write both of these equations at the same time, which is going to save us space and time. And you know, physicists are lazy, so especially me. So yeah, that's how I'm going to do it. Now, what we would like to see is if this, for some reason, shares or these eigenfunctions with L squared and Lz, because that would be very useful. So let's just check it and see if we are lucky, or maybe not so lucky because this may have been chosen for that. Okay, so if this shares the eigenfunction, this means that if we have this L squared acting on L plus minus f, this should give us just some number times L plus minus f, right? This would mean that this operator acting on f is an eigenfunction of L squared, right? Because this is just some vector, this is just some vector, they are the same vector, and this is just separated by some constant, which is the eigenvalue. So this is just the normal eigenvalue and eigenfunction equation. So let's take a look at this. Now, how could we proceed? Well, if we knew if L squared and this L plus minus commute, we could flip them, and then we know what L squared does to f. It just gives us this lambda, right? So we want to see if this is true. So let us for now erase it, because that's something that we would like to get to. And now see if L squared and L plus minus commute. Remember, what is the shape of L squared? I mean L plus minus, that's just Lx plus minus I Ly. But this is the same as just saying commutator of L squared and Lx plus or minus I, the commutator of L squared and Ly. But we know that L squared commutes with Lx and with Ly, so both of these quantities are 0. So this commutator is also 0, which means that they commute. And why is that important? That's important because since it commutes, we can now rewrite this as L plus or minus L squared f. We can reverse the order of these operators because they commute. And we know that f is an eigenfunction of L squared. So when it acts on it, we are going to get the eigenvalue acting on this eigenfunction. And since this is just a constant, we can now factor it out. And we're going to get lambda times L plus or minus f. So this is the result that we wanted. This is the left-hand side, this is the right-hand side. And this is of the form of this eigenvalue equation. So this means that when this new operator L plus or minus, for which we don't really know much at this point, but all we know is that this is when this acts on an eigenfunction of L squared, the result is also going to be an eigenfunction of L squared. That's what we just proved. And for now, it may not be quite clear why that's important, and that's fine. It's going to be much clearer later on. So now that we saw that, we would also like to know if the same way that this quantity right here is an eigenfunction of L squared, we know that it's also an eigenfunction for Lz, right? Because L squared and Lz commute, right? We can see that it's always coming back to these facts, to these commutators. Since they commute, they have the same eigenfunctions. So if L plus minus f was an eigenfunction for L squared, then it should also be an eigenfunction for Lz. So from this, it means that Lz, L plus or minus f, this should also give us some constant. This is not a 0, this is just a circle, times times L plus or minus f. So let us now work with this and try to determine if we can learn anything about that constant. Now here we have to apply a trick because we have Lz and L plus or minus. So if we now, because we don't know how this L plus or minus affects this eigenfunction, but we do know how Lz affects this, because we saw that Lz times f, this is going to be just some constant that we called mu times f. Okay, so we know what this does, but we don't know what this part does. So let us now go ahead and subtract L plus minus and Lz times f and also add it, because that way we are not doing anything illegal. This is just 0. And why is this relevant? Because now this part right here, this is Lz times f, which is just mu times f, right? Because that's what we see from this equation, and well with the L plus or minus. And this part right here is actually going to be a commutator, because just take a look at this. This is going to be Lz L plus or minus minus L plus or minus Lz acting on f plus L plus or minus Lz acting on f. I'm not going to set it in just now. And this right here is going to be the commutator between Lz and L plus or minus acting on f plus L plus or minus Lz acting on f. Okay, so to proceed, we need to find this commutator right here. So let's go for it. So the commutator between Lz and L plus or minus. So this is going to be Lz, and this is going to be L plus or minus minus L plus or minus Lz. So what is L plus or minus? Remember, this is going to be Lz, and this is going to be Lx plus or minus Ily minus Lx plus or minus Ily Lz. So let us now just distribute these products. So we get Lz Lx, then we have plus or minus I Lz Ly minus Lx Lz. And notice we had plus or minus, but we have a minus sign multiplying. So if it was a plus, now it's going to be a minus. And if it was a minus, now it's going to be a plus. And then we have Ily Lz. Okay, so what do we have here? So we have Lz Lx minus Lx Lz. This looks a lot like the commutator of Lz and Lx, right? First part Lz Lx, second part minus Lx Lz. And what do we have then? We have Lz Ly. First of all, we have a y. We're going to have a y factoring, and then we have plus or minus Lz Ly, and in this part we have minus or plus. This is going to be Ly Lz. Whoops, I went a little bit down. So this is looking a lot like a commutator as well, except of course for the fact that it's going to have these plus or minuses that we now need to deal with, and that can be quite confusing the first time around. So let's go for it together. First, this right here is just I h bar Ly. Okay, then we have this part right here. So we have plus I. And what do we have? Maybe I'm going to use something else. This. Okay. Here, let us factor out plus or minus from this part. So we get Lz Ly. And if this is a plus, this is supposed to be a minus. So if we have a minus in here, then that's going to be true. And if this is a minus, then this should be a plus. So it will be minus minus, and this would be respected. So in order for us to factor out this plus or minus, we need to replace this by a minus. Okay, and the way for you to make sure that this is correct is just to go ahead and multiply this in. So this would be plus or minus, that's fine. And in the case where this is a plus, this is a minus, and if this is a minus, this is a plus. So this would be minus plus, which is exactly what we had here, so that's fine. And now, this right here is the commutator between Lz and Ly. So that's going to be Lz, comma, Ly. But what is the commutator of Lz and Ly? Actually, I'm going to now make the notation cleaner here, so it's plus or minus I times this commutator. And what is this commutator? This is zy, this is going in the wrong direction. So this will be minus I h bar Lx. And now we have the product of two i's, which will be minus 1, but we already have a minus, so that actually cancels out. Okay, we are making progress. Now we can factor out the h bar, so we get h bar factor of I Ly plus or minus Lx. And this is actually looking a lot like the L plus minus operator, because L plus minus is Lx plus or minus I Ly. So the difference is this plus or minus. So let's factor out plus or minus from this. So we get plus or minus h bar factor of Lx. And let's see. If this is a plus, this is supposed to be a plus. So we put a plus. If this is a minus, this is supposed to be a plus anyways. So we have to put a minus sign in here to make sure that we are not changing anything. So this will be I Ly. But this right here is simply the L plus minus operator. So we get plus or minus h bar L plus or minus. So this is the result of this commutator. It's just plus or minus h bar L plus or minus. Okay, let's now go back. Let me see. Okay, this is where I wanted to set it in. So this is where we were, right? We were looking for, basically seeing if this L plus or minus f was still an eigenfunction for Lz, which it should be, but we are now checking it and seeing what information we can get from that. So let's now set this in. So this is plus or minus h bar L plus or minus acting on f. And here we have plus this part right here. Let me now set in what we know. This is L plus or minus times mu f. This is the eigenvalue of Lz. So we can now commute this with this operator because this is simply some scalar. So we get mu L plus or minus f. And now take a look at this. We have the same function here, so we can actually factor it out. So we get mu plus or minus h bar, and all of this multiplied or acting on this L plus or minus f. And this is just, remember what we started with, L plus or minus f. So now let us interpret a little bit what we found and talk about it. So remember, Lz, when it acts on some function, it tells us what the angular momentum in that direction is. Okay? And now, if f is some eigenfunction of this Lz, that means that if Lz acts on f, we're going to get mu f, which means in this case, this f state has a value of angular momentum in the z direction of mu or mu. I'm not sure I'm pronouncing it correctly, but that's its eigenvalue, that's its value. But now if we let Lz, basically if we measure the angular momentum for a state in which this L plus or minus operator acted, now our value is not mu. Now our value is mu with either plus h bar or minus h bar, depending on whether this was the plus or the minus operator. That means that now our angular momentum will be either greater by h bar or lower by minus h bar, or actually lower by h bar, I think. So that is what this tells us. And this is why we call this a ladder. This is the ladder technique, and that's why these are the ladder operators, because when you apply the L plus to some state, you get a state with a higher angular momentum. So let's actually go ahead and maybe make a quick sketch of this situation. So let's say that we have some state, right? And we know that for f, we have an angular momentum of mu. And now let us, to this state, apply the L plus, which is going to be the raising operator. Now its angular momentum will be mu plus h bar. And if we apply it again, right, we apply it twice, we're going to get mu plus 2h bar. And well, and it's going to continue that way. And if we apply L minus f, we're going to get a state with angular momentum mu minus h bar. And if we apply it twice, we're going to get a state with mu minus 2h bar. We might not know what the values of mu is for now, but we know that whatever it is, these operators of L plus and L minus allow us to go for lower or higher values of this angular momentum. Okay, so that's where we are at right now. But, and by the way, this is also why this is called the ladder. That's why it's ladder operators, because this looks like a ladder. That's simply why. But now we have to think about it. We can't really just apply L plus to f forever. At some point, if we're just going higher and higher, eventually the angular momentum for Lz would exceed the total angular momentum, and that doesn't make sense. So there has to be some top level that satisfies that when you apply the raising operator to it, you get 0. So at some point you can't have a higher angular momentum for a fixed total angular momentum. So there has to be some state here, which we call ft, because that's like the top state. And for this particular one, and this is a very important part, at least it confused me the first time around, so let's maybe discuss it a little bit. Where were we here? We know that if we have L squared acting on some state f, we get some constant times f. And if we have L squared acting on some other state that has been changed by either L plus or L minus, we also get an eigenvalue of lambda. This means that applying the L plus or L minus operators, the raising or lowering operators, they do not change the value of L squared. That's very important. So if we are looking now at this topmost state and we apply L squared to it, we are going to get the same value that we got for just the f state, and some random state in between, that is the one that we have been looking at. So this lambda is going to be the same. However, the Lz, this is not going to be the same, acting on ft. This is not going to be the same, of course, because we are increasing it. And we are increasing its value by multiples of h bar. So that means if we can only go back up and down by multiples of h bar, then that means that the top level will be some multiple of h bar. Okay, so let's just call it h bar L. Okay, and this is going to be acting on ft. So this is the part where you have to understand the logic behind this. Okay, it's very, very important, because the next step is quite simple, but if you understand this logic, that's fine. So since here this condition that we know is that this L squared is basically constant here, let us now attempt to rewrite this. Now, there is the following thing that we have to use. It's kind of a trick, and it goes as follows. We're going to multiply L plus or minus by L minus or plus. This is going to give us two forms to rewrite L squared that are going to be very useful. So this is going to be Lx plus or minus I Ly times Lx minus plus I Ly. So let's multiply through, we get Lx squared, then we get minus plus I Lx Ly plus or minus I Ly Lx. And now let's take a look at this. If we have plus times minus, we get minus. If we have minus times plus, we get minus. So either way, we're going to get a minus here. But then we have I times I, which is going to be minus. So we're going to end up with something positive. And then we have Ly squared. And notice that here we have Lx squared plus Ly squared. And L squared is Lx squared plus Ly squared plus Lz squared. So what we have here, which is Lx squared plus Ly squared, this is simply L squared minus Lz squared. Right? This just comes from here. So let's actually write it that way. So this is going to be L squared minus Lz squared. And then we have these things here. What can we do with that? That's Lx, Ly, Ly, Lx. So that's kind of looking commutatory. It looks like a commutator. So let's begin by factoring out the I. So let's just say plus I. What can we do now? There's this plus minus, this minus plus. So let's maybe try to factor out the plus or minus sign and see if this does any good. I'm going to use this parenthesis not to confuse it with a commutator. So then we have, for this part, it's Ly, Lx. And if this is a plus, this has to be a minus. And if this is a minus, okay, so we need a minus sign in here for this to make sense, similar as before. Minus Lx, Ly. You can either now rearrange this for this to be the commutator of Lx and Ly. I'm actually going to use this opportunity to write this the following way. So this is going to be Lx and, oh, sorry, the other way around. This is Ly, comma, Lx. So, well, we have actually seen it before. I thought we hadn't for some reason. This is just going to be minus I h bar Lz. And since we have I and I here, right, we have these two i's, it's going to be another minus sign, which will cancel out this one. So we're going to be left with h bar Lz here. And this is equal to L plus minus L minus plus. So from here we can now find and see that L squared is going to be equal to, let's see, L plus minus L minus plus. And now we have plus Lz squared. And then we have minus or plus h bar Lz. I had to flip this because now we have to subtract by this quantity, so this changed. Okay, so this is what we wanted to find. We now have a way to rewrite the total angular momentum squared. So let us now plug it in here. So instead of this L squared times this top function, we are going to get, there's two possibilities now, because remember, these are two equations, either with a plus and minus here or with a minus and plus. If we take the minus and plus, we are going to get L plus acting on Ft, and that is 0. So that is simple. We like that. So let us take that case. So we get L minus L plus, this is going to be acting on Ft, plus Lz squared minus or plus h bar Lz, and all of this is acting on Ft. And now I'm going to change colors. I don't really like red. Okay, so this is going to be, this acting on Ft is 0. That's why we chose this version, because it's going to give us something that is 0, and we like that. Then we have Lz squared acting on this Ft. That's basically Lz acting on Lz Ft. But what is Lz Ft? That's simply h bar L Ft. So we can write it like that. So this is going to be acting on h bar L Ft. But you can actually now just take h bar L outside and let Lz act on Ft once again. And what does that give us? Another h bar L Ft. So that's going to give us h bar squared L squared times this Ft. You see how important it is to understand well the concepts of commutators and eigenvalues and eigenfunctions here. Now we have this h bar squared L squared Ft. Now we have this minus or plus. Well, and what do we do with this minus or plus? We already chose, and actually I shouldn't have written like this before because we had chosen the plus sign. So sorry about that. This is going to be plus h bar And what is LZ acting on Ft? That's just h bar L. So it's going to be h bar L acting on Ft. So here we can now factor, this is just h squared, by the way. So now we can factor out h square L, and we get L plus 1 Ft. Okay, so this is the value, this is what we get when we let L squared act on Ft. But remember, this has to be the same as lambda Ft, because this value for lambda was unchanged. So now we can actually see that lambda is h squared L plus 1. There we go. Okay, so this is the value for this lambda. It's still in terms of this L that we don't know too much about, right? L we just know is basically how many times we have gone up, but we are going to learn more about it. So we saw this top level. Now let us take a look at the bottom one. Now, what is the bottom one? Well, there has to be some point where if we apply this lowering operator, where we get a state that is 0, right? Similarly, as we had before, we can't go infinitely up, we can't go infinitely down either. And in this case, L squared acting on this bottom state also has to give us lambda Fb, and we now know what lambda is. And if we apply now the operator for Lz on this, we are going to have to get, once again, some multiple of h bar, and this time let's call it k. K is basically the amount of times that we have gone down. And this is going to be acting on Fb. Okay, so let's do the same that we did before. So let's, in this equation, write the expression that we just found. So let's use, where is it? This. So L squared is going to be this. And this time, what is 0? 0 is L plus L minus when acting on F bottom, because L minus acting on F bottom is 0. So we want to use here the expression that is L plus L minus plus Lz squared minus h bar squared Lz. So let me go and put that in. So L squared Fb, this is going to be, I think it was L plus L minus plus Lz squared minus h bar Lz, all of this acting on Fb. And as we saw, this is 0 when acting on Fb because of this, right? This is the bottom rank. There, we don't get anything if we apply the lowering operator here. Okay, so we get that, then we have Lz squared acting on this Fb, and that is just going to be this squared. So similarly as before, it's going to give us h bar squared k squared, because we're applying this twice onto this Fb. And now we have minus h bar, and what is this Lz acting on this? It's just h bar k, so we get h bar squared k Fb. So if we factor here our terms, we get h bar squared k times k minus 1 Fb. And this has to be the same as lambda Fb, but we know that lambda is h bar squared L plus 1. So now from this we can see that h bar squared k minus 1 has to be the same as h bar squared lambda plus 1. So we can here cancel out the h bar squares and put everything else to one side, let's say the left side. So we get k squared minus k minus L squared minus L is equal to 0. And here we can factor out some things. So we can put k squared and minus L squared. We can write it as k plus L, k minus L, and then we get minus k plus L. So here we can factor out, k plus L, and this is going to be a factor of k minus L from here, and then we still have minus 1 time, so minus 1. This has to be equal to 0. So for this to be true, k has to be equal to minus L, or k has to be equal to L plus 1. But let's think about what this means. K is this lower level, and this basically tells us that this k is higher than the highest level. That doesn't make sense. So this is not a possible solution. So the only possible solution is that k is equal to minus L. So that tells us if the top level is at L, then the bottom one is at minus L. And that's actually very, very interesting, because let's go back to this drawing here. This means that the bottom level here, FB, will have, as we saw, some energy that's going to be, what did I call it? Minus L H bar. And the top one will be FT, and that's going to be L H bar. So we can see that we go from minus L to L, and we go in integer steps of H bar. So basically we are going from minus L, and then we go n steps, and we get to L. So from here we can actually see that these n steps are going to be 2 times whatever L is. And from here we can see that L is going to be n divided by 2. And why is this interesting? This is interesting because n is an integer, any integer. So this means that L right here is going to be, what are its values? It can be 0 because there could be 0 steps. It can be 1/2 because there could be 1 step. It could be 1 if there are 2 steps. It could be 3/2 if there are 3 steps. It can be 2, it can be 5/2, and so on. So it basically can be any half integer or integer. So those are the allowed values for L. What about now these other values for what we call mu minus 2h? This notation is maybe kind of not so good. So let's come up with a new one. So if we are measuring the angular momentum of some state, let's now call it its eigenvalue m times h bar, right? Because we know that it's going to be multiplied by h bar, and m is going to be a number that goes from minus L to L, right? Because we know that its lowest level is minus LH bar, and its highest level is LH bar. Okay, so we now have determined the eigenvalues of both L squared, because L squared of some f we now see is h bar squared L plus 1. So we know that its eigenvalue is this right here. It depends on L, and we know that the angular momentum in the z direction is going to be m h bar. So, and there are going to be several possibilities for the values of m and L that depend on the physical system that we are dealing with. So basically these eigenfunctions will actually depend on L and m. And we are going to do maybe 1 or 2 problems in the next video, and then we're going to start with the task of determining what the eigenfunctions are. So this is it for this video. Let's just go ahead and do a quick recap. So what we did is we defined the angular momentum as the classical angular momentum that we have seen, except that we used this h bar over I for the momentum. We then just did a cross product, and we found what these Lx, Ly, Lz are, and we saw that they do not commute. So we wanted to find some other operator that commutes with them, and we saw that the angular momentum squared commutes with each one of these angular momentums, so we chose any, so we chose Lz. And then we set out for the task of finding what its eigenvalues, lambda for in the case of L squared, and mu for the case of Lz, what they are. And for that we used this ladder operator process that I just discussed. So that's why we are now done, just in case anyone maybe got lost in the process. So I will see you in the next video.